typically weight is removed of this cup. Okay, this is 7.98. Okay, so next I'm going to measure the R1 and R2, which is this side, which is this plane here. 4 point. Right, she's on, and the crankshaft weighs 12.6. Quickly here, because what we need to do is we need to Hey guys, welcome back to the channel and to another video. This is part 2 of the dynamic crankshaft balancing. Enjoy. Yeah guys, so I'm ready to put the dart into the machine. As you can see here, we are on a double plane page because the last job that I done was a double plane. If you've been watching my videos, you'll notice that on the vacuum element that was a double plane, and I've been doing a few vacuum elements, so this page was actually quite relevant for this job now. So I'm going to be sticking in the information. This is a double plane, so like it's the same as on the vacuum. I'm going to be measuring from the center of this journal to the center of the roller. That would be A. I'll be measuring from the center of this journal to the center of that roller there. That will be B. I mean, that will be C, and B will be from this center to that center. That's the measurements that I'm going to do here. Then R1 will be the height from this journal down to the main bearing there. I'll take this diameter of the main bearing divided by 2, and that radius I'll add to that height there. That would be okay. So R2 will be from this side down there to there. Also the diameter divided by 2 plus that height, that will give you the R2. That information I'll stick into the crankshaft, into the data now. Let me just select the page quickly. Okay, so selecting the page. Once again, I'll go up to the measure. I'll run a stop there. I'll go to the rotor, and I'll click plus because I'm looking for a new page. That would come up there, and I'll call this job crankshaft. Okay, I'm on cap locks. Let me just get off that quickly. I'll call the job crankshaft. Okay, there we go. And once again, this is a double plane. This is a double plane job, which is that configuration over there. So I'll stick in 1 here, which shows obviously that over there. And this is where I'm going to fill in all the information. So what you do here with the speed, this is the speed that the crankshaft will be performing at once assembled in the engine. And I'm not saying by putting speed you must put in you know, the idle or something like that. You put in like the mid-range of the rev of the engine, because most engines, in my opinion, I speak under correction, most engines have a critical point of about 3,800 to 4,000 revs. That's when most of the unbalance in the engine takes place, through that range. And most engines kind of run at you know, 6,000 revs or something like that. You get those oaks that really push it 8,000, but that's also not running continuously for 8,000. So if you look at a rev that the engine's continuously running at, it would be more or less, you know, it would be more or less about 6,000, you know, 6 around about there. So for your operating speed, I'll put in 6,000. There I'll put in 6,000. on your operating speed. Okay, so it's also worth noting that when you do the operating speed of which the crankshaft will be operating at, obviously once assembled, you build the engine will be built for a certain thing. So if it's a race engine and it will be running at 7,000 most of the time, 8,000 most of the time, and you change that to 8,000, you know, that's where it will be peaking at, or 7,000. Like 6,000 is actually also a bit high for a normal road car. If you build in just a normal road car engine, you know, 6,000 is also a bit too high, because at 6,000 you'll be breaking the speed limit already. You know, you probably have to put in 5,000 or something like that there. So I think for the sake of this video, let's say we're building a road car, I'll actually change this to 5,000, because I think for, you know, petrol engine running at 5,000, you probably will be doing, you know, a fair speed in the hundreds, and that's when the engine will be working the most, at 5,000. So let's change that to 5,000. I think it makes a little bit more sense there. And I'm just going to capture all this data here. But like I said, I'll show you the process. Like at 5,000 doesn't stay there. That is, you're just telling the computer now for its algorithms that this engine peak rev, or this engine will be working at 5,000. So anyway, let me just put in the rest of the data. Okay, so let's just remove this crankshaft quickly here, because what we need to do is we need to capture the weight of it as well. So let me just remove this crankshaft very quickly and stick it on the scale and see what it weighs. Okay. Right. Let's put the scale on. I already put this board on here, just to make sure it's on 0. Okay. Right, she's on, and the crankshaft weighs 12.665 kilograms. Let me just get that on the board quickly. Right here. 12. Okay, that's what the crankshaft weighs, and it's cast iron as well. So okay, this is 7.980, and that is actually grams per centimeter cubed for the techno guys. Okay, so I got the weight, got the density. I can stick the crankshaft back in now, capture the rest. Okay, she's back in now. So now let's start capturing the data. So this doesn't have to be like super accurate, these distances across here, you know, the A's, the B's and the C's doesn't have to be like super accurate, because the crankshaft floats as it spins on this machine. So you know that distance from there to that center will, it's not a steady difference, so that you can measure the tape measure that section here with a vernier. Okay, got my tape measure. First measurement would be A, which will be the center of the roller to the center of the crank, and it kind of looks like it could be 21. So let's just stick that in here. So A, make it 21. B, be the distance from there to there. See, more or less there from the center there to the center here. Oh, it's kind of difficult with one hand, but it looks as if it's 355. Yeah, it could be 355. Let's stick that in. 355. C will be this section here. So more or less from the center there to that center there, I'll say that's 20 millimeter. 20 millimeter. So that the A was 21, B's 20, and C's 20. Doesn't mean that there's something wrong. It just means that this is sitting 1 millimeter closer that way, and that's sitting 1 millimeter further. But like I said, this floats as it runs, so that's not something to panic about. Then you do your R1. I'll just get my vernier. Oh, it's not here. Okay, I can use the small one. Just use this small one here. Just get a bigger vernier because the section's a little bit too short. Okay, so I got my 300mm vernier because this area is nice and big down there. So let's just do. I'll just measure it one side because these should be the same. The main bearing should be the same. So obviously the radius should be the same there. This distance from there to there should be the same. Or maybe vary by a little decimal, but that's irrelevant. So whatever R1 is, R2 should be as well. So this is 56.8, and half of that would be 28.4. That would be the radius of the main journal, and then you must add the what's his name, this height here, and that is 34.4. Say 34.4 here. 34.4. That's obviously 8. That's 12. 3 and 3 is 6. So it's 62.8. So R1 would be 62.8, and R2 is also 62.8. If that varies a lot, then there's something drastically wrong with the crankshaft. But it's good to double check. So I'll just do the odd double check in quickly. Obviously the main bearing should be the same. And this here, yep, that's about 34 point. Yeah, this is 3 whatever, but doesn't matter. Okay, so I got R1 and R2. I'm going to fold that into the machine. Yeah, guys, I'm ending this one here, guys. I'll be carrying on with the capturing in the next video. Some more of the capturing in the next video. I hope you enjoyed it thus far. Don't forget to like, subscribe, press the notification bell, not to miss out on the next video. And I'll catch you on the next one. Cheers for now.
Did anybody out there hear me?